Proof method and strategy. Proof by cases. This method relies on the equivalence P1 or P2. If this, then Q is equivalent to if P1 then Q, and if P2 then Q. To prove some theorem like this directly, we prove first that if P1 then Q is true, and then if P2 then Q is true, then the equivalence guarantees that the original theorem is true. First, we'll prove this equivalence. We use this equivalence if P then Q is equivalent to not P or Q, the De Morgan law, and one of the distributive laws that we know. This equivalence, if P1 or P2 then Q, is equivalent to the negation of P1 or PQ or Q. The negation of this junction is conjunction of negated P1 and P2. So this in parentheses or Q. Now distributive law applies, not P1 or Q in parentheses and not P2 or Q. But in the first parenthesis, the expression is equivalent to if P1 then Q, and the expression in the second parenthesis here is equivalent to if P2 then Q. So establish the equivalence that you want. Example 1. Prove that if x and y are real numbers, then the maximum of x and y is equal to x plus y plus the absolute value of x minus y, all this divided by 2. We have, for any two real numbers x and y, we have three possibilities, that is, three cases. Either x is equal to y, or x is bigger than y, or x is smaller than y. So we consider these three cases. So instead of two cases as in the equivalence, we'll have three cases, but it can be proved the same way. In the first case, x equals y, x and y are equal, so the maximum is equal to x. The right-hand side of the equality that we want to establish is this. When x and y are equal, this is 2x and this is 0. 2x divided by 2 is x, so we have equality. Both sides have value x. In case 2, x bigger than y. The maximum of x and y is equal to x, because it is bigger. The right-hand side now is this, because x bigger than y means that x minus y is positive, and the absolute value is just the same number. Now this is 2x over 2, which is just x. So I get the same result. The equality is established in this case 2. In the last case 3, x less than y. Now the maximum of two numbers is y. Y is the bigger number. The right hand side is equal to, now x is smaller, so x minus y. X is smaller than y, x minus y is negative, so the absolute value of a negative number is negate that number, you get a positive number. Negate x minus y. Evaluate the numerator, now it is 2y. 2y divided by 2 is y. And we get the same result. So the equality is established again. And this completes the proof by cases. Without loss of generality. When the phrase without loss of generality is used in a proof, we assert that by providing one case of a theorem, by proving one case of a theorem, no additional argument is required to prove other special cases. So they can be proved the same way as the case that we consider. Example, show that if x and y are integers and both x times y and x plus y are even, then both x and y are even. Proof. We use proof by contraposition. Proof by contraposition. Suppose that x and y are not both even. The negation of the conclusion here. That is, we assume that x is odd, or y is odd, or both. Without loss of generality, we assume that x is odd, so that x is equal to 2m plus 1 for some integer m. To complete the proof, we need to show that the negation of this is true, which means x times y is odd, or x plus y is odd. We consider two cases, y is even and y is odd. In the first case, y is even, so y is equal to 2 times n for some integer n. Now x plus y is 2m plus 1 plus 2n. It can be written this way, which shows that x plus y is odd. So we have what we wanted in this case. In the second case, y is odd. So y is 2n plus 1 for some n, some integer n, so that xy now is this product, multiply out and factor out 2 for the terms that contain 2 as a factor, we get this. This shows that xy is an odd number. 2 times an integer plus 1, odd number. And this completes the proof. xy in this case is odd. Proof strategy in action. The discovery process in mathematics begins with exploring concepts and examples, asking questions, formulating conjectures, and attempting to settle these conjectures either by proof or by counterexample. Tiling. In this example, we consider checkerboards. A standard checkerboard contains 8 rows and 8 columns. A board will refer to a checkerboard of any rectangular size, as part of checkerboards obtained by removing one or more squares. A domino is a rectangular piece that is 1 square by 2 squares. We say that a board is tiled by dominoes if all its squares are covered with no overlapping dominoes and no dominoes overhanging the board. Example: can we tile a standard checkerboard using dominoes? Everybody can find a solution to this easy problem. Another example: can we tile a board obtained by removing the upper left and the lower right corner squares of a standard 8 by 8 checkered board using dominoes? Solution: we can try and we cannot cover the board. How can prove that a tiling does not exist? There are too many cases to consider here, so solution by proof by cases is not feasible. Observe that a domino in a tiling covers 1 black and 1 white squares. The number of black squares is different from the number of white squares because the removed corner squares have the same color. Hence, a tiling for the board does not exist. Example: the 3x plus 1 conjecture. This is a problem that is easy to describe but has not been solved by anybody. Let n be the set of all positive integers and t be the function from n to n described here. T of x is f of x over 2 if x is even, and T of x is 3x plus 1 if x is odd. Proof or disprove the following statement. For all positive integers x, when we repeatedly apply the function t, we will eventually reach the integer 1. Example: if we start at the integer 5, t of 5 is 3 times 5 plus 1 because 5 is odd. We use the second row. 3 times 5 plus 1 is 16. T of 16. Now 16 is even. We must use the first row. T of 16 is 8. Because 8 is even, the first row applies again. T of 8 is 4, T of 4 is 2, T of 2 is 1, so we reach 1. So the conjecture is true for 5. Check that it is true for 6. It is checked for many positive integers. It's always true, but nobody was successful to proving that the conjecture is true for all positive integers, or to find a counterexample. Another problem, prove or disprove that if you have an 8-gallon jug of water, full of water, and 2 empty jugs with capacities of 5 gallons and 3 gallons, then you can measure 4 gallons by successively pouring some or all of the water in a jug into another jug. Solution. Here, this triple means the amount of water in the 8-gallon jug, 5-gallon jug, and the 3-gallon jug. So in the beginning, the 5-gallon and 3-gallon jugs are empty, so you have zeros there. And the 8-gallon jug is full, we have an 8. Then we can fill out the 5-gallon jug. We get come to this configuration. Then use the 5-gallon jug to fill out the 3-gallon jug. You arrive at this configuration. Now, pour all of the water from the 3-gallon jug into the 8-gallon jug. You arrive at this configuration. Then fill out the empty the 5-gallon jug into the 3-gallon jug. Since we have only 2 gallons here, we'll have 2 gallons in the of water in the 3-gallon jug. So I arrive at this configuration. Then use the water from the 8-gallon jug to fill up the 5-gallon jug. You arrive at this configuration. Now, in the 3-gallon jug we have 2 gallons of water, so use the 5-gallon jug to fill it, to fill up the 3-gallon jug. Well, you need only 1 gallon to fill the 3-gallon jug. Here, this way, in the 5-gallon jug, you'll have 4 gallons of water remaining, and the problem is solved.